Welcome to our fourth lesson on acids and bases. Now during this lesson we're going to be taking a look at your neutralization reactions of acids and bases again, as well as your titration calculations. Now let's start off again by taking a look at the different type of reactions that your acid can undergo. If we start off with having an acid and a metal, the common type of products formed will be salt and hydrogen gas. Now let's take a look at an example. We're going to be using hydrochloric acid here as our acid, and then we'll be making use of zinc as our metal. Now acid is going to end up forming salt and hydrogen gas. Now this salt is not necessarily your table salt, which is NaCl. This salt is just any two metal and non-metal ions that combined. And remember, metals is positively charged ions, non-metals negative, so positive and a negative ion that combines gives us a salt. Our hydrogen gas, though, we know will always be H2 because hydrogen gas is seen as a diatomic molecule and therefore will always be two of the same atoms attached. Okay, now finding our salt. Your salt will always come from a positive and a negative. And the positive, which will always be the metal, will be written first, followed by the negative ion, which will always be a non-metal. Now taking a look at the type of metals and non-metals given. The metal that we are going to be making use of in our salt is going to come from Zn, because we said that's the metal that we're using. So we're going to have Zn, but it must be in its ionic form, and then a non-metal attached to this. Now our non-metal must be negatively charged. Now remember, our hydrogen is positively charged, but our chloride is negatively charged. So that means our chloride is going to be our second part of our salt. Now do remember that the charge on our zinc metal is 2+, and as we said that on chloride is 1-. So when we combine the two, we'll note though that we'll need another chloride ion to completely cancel out the two positive charges of Zn. So our salt will end up being Zn and then two chloride ions, so that's how come it's going to have a small subscript 2 at the bottom. So our salt is going to be zinc chloride. Let's go and take a look at another type of reaction. An acid in this case and a metal oxide. Now that means it's any metal that's attached to oxygen, and it is going to be seen as a base. All metal oxides, and you'll see again metal hydroxides, is seen as bases, and they will form those salt and water. Now once again, this salt is not your table salt. It is actually a positive and a negative ion that combined. Now as our example, we're going to use sulfuric acid and as metal oxide, magnesium oxide. Now we know that it's going to form a salt and water. Now water, at least you know, is H2O. Let's go and figure out what will the salt be. The salt is made up of a positive metal ion as well as a negative non-metal ion. Now obviously when we start off here, we'll have our metal oxide, and the metal ion here is my magnesium 2+. My non-metal ion will always come from the acid, and this is going to be our SO4, and SO4 found by itself is SO4 2-. That means my salt is going to be magnesium 2+, and the sulfate ion of 2-. They cancel each other out charge-wise to end up giving me MgSO4 as my salt. Now let's take a look at the third type of reaction, where we're going to have an acid and a metal hydroxide. And this hydroxide is going to be coming from a base once again. As I said, our metal oxides and metal hydroxides are seen as bases. Okay, now let's go and take a look. As our example, we're going to be using nitric acid, and as our metal hydroxide, we're going to be using calcium hydroxide. Now we know that a salt will form and water we have is H2O. Let's go and determine our salt. Our salt is made up of a positive metal ion, and therefore it's going to be our calcium, and a non-metal ion, which is negative, and that will always be coming from our acid. So it's going to be the calcium and the nitrate that combines to form the salt, noting that the calcium, which is the metal, will always get written first, followed then by the non-metal. But our calcium is a charge of 2+, our nitrate ion is a charge of 1-. So once again, we're going to need two nitrates to completely cancel out the two positives of calcium. So we're going to be having our nitrate in brackets with a 2 at the end. Now, just to remind you again, we will discuss it in detail when we get to the pH calculations. Whenever you have an acid and a base, it will give you a salt and water. And as we said, that base can be either metal oxide or a metal hydroxide. And this is known as a neutralization reaction. And the pH at the end of such a reaction will be 7. Now, our last type of reaction with an acid can be that between an acid and a metal carbonate. And that will produce 3 products: salt, water, and carbon dioxide gas. Okay, now let's go make use of hydrochloric acid as an example, and our metal carbonate as calcium carbonate. Now, when they react, we know a salt's going to form. We'll figure out the salt right now, but we also know that it will be water and carbon dioxide gas. So there's my 2 products. Let's go and see what will be the salt at the end of this reaction. Once again, it's going to consist of a metal ion and a non-metal ion. Our metal ion is going to be our calcium ion, that's 2+. Non-metal ion always comes from the acid, and that's your Cl-. Now note that our calcium is 2+. Therefore, we'll need 2 of my negative chloride ions to end up cancelling out the 2 positives of my calcium. So calcium chloride is, in this case, the salt. Now let's quickly revise our titrations again. During our titration, you'll have an acid. The acid usually has a pH of less than 7. And then we'll take a look at a base which we'll add to that, and that is usually a pH of higher than 7. As we already have just seen, when we add an acid and a base together, we're going to get salt and water, and that's going to give us a neutral pH of 7. So this neutralization reaction can happen while we do a titration. Now let's take a look again at the apparatus of our titration. We're going to be having an Erlenmeyer flask here at the bottom that will contain a base. Now we're going to add in an indicator, and remember, depending on what the color is of the indicator, it will tell us whether it's an acid or a base inside of here. Good, and then we're going to have a burette, and we'll add acid to the burette. Our burette usually measures the acid in a volume of cubic centimeters, and then we'll dropwise add our acid to the base until our indicator will tell us it's a neutral solution via the color that it changes. And then if we should add 1 drop more, we'll realize that now suddenly it becomes an acidic solution, and then the color change of the indicator will once again be different. Now there's a specific formula that we make use of when we take a look at titration calculations. This formula is given to you, and it states that N, which stands for moles of the A, which is for acid, divides by the moles of the B for base, is equal to the concentration times the volume. Remember, concentration is a small letter, volume a capital letter, of an acid, divided by the concentration times the volume of a base. Now just to quickly remind you again, this number of moles is not the value you're going to calculate. You're going to get it from the mole ratios in front of your acids and bases in a balanced reaction. Now just to make sure you understand, here's an example. We've got sulfuric acid plus sodium hydroxide. That would end up giving us a salt of sodium sulfate and water. Now when we balance this reaction, we realize that we have to place a 2 here in front of the sodium hydroxide. Now we know that our H2SO4 is our acid and our NaOH is going to be our base. And that means when we take a look at this mole numbers Na and Nb, we're going to take a look at the mole ratios in the front of these acids and bases. In front of my acid there's nothing, and that basically indicates a 1. So it's going to be 1 over, and then in front of my base though there's a 2. So it means we're going to have a 2 for Nb. So our Na over Nb is actually in this case going to be 1 over 2. Now let's quickly apply this to an example. We're going to have sodium hydroxide base with a volume of 25 cubic decimeters, and it has a concentration of 0.5 mole per cubic decimeter. It's then going to be titrated with 15 cubic decimeters of hydrochloric acid when it reached an end point. Now an end point means that's the point where we're actually going to neutralize, and the pH is going to be back to 7 because we've got a strong acid and a strong base, but we'll talk about that again a bit later. What we would like you to go and do is to go and calculate the concentration of the hydrochloric acid. Now we're going to quickly write down from this a balanced chemical equation and then fill in, according to our formula, the values that was given to us. Good, so here's our equation, HCl, which is the acid, plus NaOH, which is my base. It forms for us a salt, which in this case is NaCl, and water. And it's already balanced. There is no changes to the mole ratios when we take a look at this reaction. Now here's my formula. Let's go and punch in the values that we do have. In front of my acid we've got a 1, and in front of my base also a 1. That means for my Na it's 1, and for my Nb is 1. The concentration of the acid is what they want you to go and calculate according to our question, and they've given you the volume though of the acid to be 15 cubic decimeters. They also further on went to tell you that the concentration of the base was 0.75, and that was titrated with a volume of 25 of the base. So from here onwards we can go and find the concentration to be 1.25 mole per cubic decimeters.